Okay, what I'm going to do is I'm going to run through with you how to calculate a limiting reactant, an excessive reactant, and a percent yield question. So I'm just going to step through this with you and kind of remind you how to do that. Okay, first of all, how will you recognize a limiting reactant stoichiometry question from just a general or plain stoichiometry question? That's actually a pretty easy question to answer. The limiting reactant stoichiometry question will usually ask you to determine the limiting reactant. So that's one big tip off. If I don't actually ask you what the limiting reactant is, you can recognize a limiting reactant stoichiometry because this kind of stoichiometric analysis always lists two given starting amounts for the reactants. So you'll have two given amounts. And that pretty much tips you off that it's limiting reactant. Anytime you have two givens, that's a limiting reactant stoichiometry question. I want to define some terms with you first about limiting reactant. First of all, a limiting reactant, also known as a limiting reagent, is a starting material in a chemical reaction that in the course of the reaction gets completely consumed or used up by the reaction. So it limits the quantity of product that can be made. On the other hand, the excessive reactant or excessive reagent is the other starting material in the chemical reaction, and this starting material is not completely consumed in the course of the reaction. At the end of the reaction, there'll be extra excessive reactant left over, so it will not get completely used up, and that's an important distinction. Limiting reactant gets completely used, the excessive reactant does not. Another term that is frequently misunderstood by students is the term theoretical yield. The theoretical yield is an amount of product predicted by the stoichiometric analysis. In fact, it's the answer to a stoichiometry problem that begins with the limiting reactant starting amount. Typically, we say the answers to stoichiometry problems are theoretical yields, but specifically when it's a limiting reactant stoichiometry question, it's the answer to the stoichiometry setup that starts with a limiting reactant. The other term that I'm going to define for you here is actual or experimental yield. Those two terms are synonymous, actual or experimental. And that's simply an amount of product that's made during an actual experiment that's massed in a lab on an analytic balance. For problems that we're going to do with stoichiometry on paper, I will use the term actual or experimental and list a mass for you in the question that is either representing the actual or experimental yield. Now, how are we going to work a limiting reactant question? First, we're going to read the reaction and write a balanced chemical equation. You're going to find the two given amounts. And when you do this, you will work two stoichiometry analyses to a product. It doesn't matter which product you work toward. Typically, I would tell you to read the whole stoichiometry question and see if it ultimately asks you to answer a particular theoretical yield for a product. And if it does, I would work both of your stoichiometries to that product. The third thing is you're going to evaluate the answers to your stoichiometric analysis, and you're going to pick the smallest answer to represent the theoretical yield of product. The fourth thing you're going to do is remember that the starting chemical for the setup that gives you the smallest yield of product represents the limiting reactant. So I'm going to show you a problem now. Given the reaction 2CH4, 2C4H10 rather, plus 13O2 yields 10H2O plus 8CO2. If you were given 15 grams of C4H10 and 25 grams of oxygen gas, determine the limiting reactant and the theoretical yield of water. Work two stoichiometry setups to a product that's water. Okay, so we start off with 15 grams of C4H10, and we calculate the formula mass in grams of C4H10, and by definition, that's equal to moles. Now that we're in terms of moles, we're going to do the stoichiometric step. Remember, the stoichiometric step involves you putting moles of the chemical you want to find out, in this case water, over moles of the chemical you're given to start with, C4H10. Okay, so I've highlighted that for you. 10 moles of water over 2 moles of C4H10. Now, to follow up, we're going to change from moles of water to grams of water by plugging in the formula mass of water and 1 mole of water. So when I do that first stoichiometric setup, I'm going to calculate by multiplying everything on top together and dividing by the product of the denominator, and I'm going to get 23.3 grams of water. Now, I would then go through the process of setting up a second stoichiometric analysis, starting with 25 grams of oxygen gas. So here would be the second setup. Okay, it's very similar, starting with 25 grams of water, 25 grams of oxygen, formula mass of oxygen, this time 10 moles of water for every 13 moles of oxygen gas, and I get to recycle and use my formula mass of water. This analysis gives 10.8 grams of water. Now, I have two stoichiometric answers. Only one of them represents the theoretical yield. We're going to choose the smallest answer to represent the theoretical yield, which would be the 10.8 grams of water. So I'm highlighting that. The theoretical yield is 10.8 grams of water. Now, the limiting reactant for this reaction is revealed by the answer that we determined for the theoretical yield. The starting chemical for this analysis was oxygen. The limiting reactant for this reaction is oxygen gas because it yielded the smallest quantity of product. The other reactant, C4H10, is called the excessive reactant. It will be left at the end of a reaction. Not every bit of it will be used, but the oxygen will be completely consumed. So you have two stoichiometries that are started because you have two givens. You find two answers. The smaller of the two answers represents the theoretical yield, and the reaction that used to set up the theoretical yield that was the smallest will reveal the limiting reactant as the starting material. Now that we've identified the limiting reactant is oxygen gas and the excessive reactant is C4H10, I'm going to give you a second question. If you were given 15 grams of C4H10 and 25 grams of oxygen gas, determine how much excessive reactant is left over at the end of the reaction. To answer this question, you must first find out how much excessive reactant is used by the stoichiometry. You're going to do a stoichiometry setup from the given amount of limiting reactant to the excessive reactant in grams. Once you have done that stoichiometry, you will subtract the excessive reactant amount used from the excessive reactant amount given to determine the leftover amount of the excessive reactant. Okay, so here is the stoichiometry. Remember, C4H10 is representing the excessive reactant, O2 is the limiting reactant. I was originally given 25 grams of oxygen gas, so I start with 25 grams of oxygen gas. I change from oxygen gas grams to moles. My stoichiometry setup is going to the excessive reactant C4H10. The coefficient 2 is from the coefficient of the balanced chemical equation. The 13 on the oxygen comes from the coefficient of the balanced chemical equation. I want to know the mass of C4H10 that was used, so I'll place the formula mass of C4H10 here at the end and place it over 1 mole. If I go through and calculate 25 times 2 times 58 equals, divided by, open parentheses, 32 times 13 equals, I will get 6.97 grams of the excessive reactant C4H10. That represents how much C4H10 was actually used in the reaction. It's not how much is left over, but it was how much was used. To figure out how much was left over, we're going to want to do a subtraction problem. We're going to take the original 15 grams of C4H10 that was given in the problem and we're going to subtract from it